Okay, hello everyone. Welcome to episode 73 of the Warsaw Quantum Computing Group meetups. My name is Pavel and I will be the moderator and host today. And we have pleasure to host our great speaker, our guest from Basel, from the University of Basel, Dr. Julien Baglio. And he will give a talk about quantum generative adversarial networks for healthcare and life sciences. Before we start, we would also like to thank our strategic partners for supporting us. So Novero R&D, Quantum.io, Onyx, Cogit, AIQ Lab, and ThinQubit. And we also thank our honorary partners for also helping us in advertising this meetup. All right, so Julian, if you are ready, first of all, thank you for accepting our invitation. It's also our pleasure to have you here for the first time. And we are looking forward to your talk, so you can try to share your slides once again.
Thank you, Pavel, for the nice introduction. Do you all see my slides?
Yes, we can see your slides. Maybe just one more announcement to the participants. If you have any questions, please raise your hand. We've agreed with Julian that we can try to ask the questions and answer the questions on the fly, and we can try to interrupt. So the meeting will be interactive, but you can also post your questions on the chat, and we can also ask them later.
Yeah,
So
thanks.
Julian, the Zoom is yours.
Thank you
Thank you.
very much. So yeah, so it's my pleasure here to present you how quantum computing and in particular quantum generative modelings could advance healthcare and life science. And it's a talk is based on multiple publications. So I've gave some references here, plus a forthcoming publication for which some of the results were presented last year in a conference in Aachen. So let's start with the executive summary. I now tend to always do that in case you are bored or in case you are tired, so that you can already have the essence of the talk. So I'm focusing here on image analysis or drug development, because both are lengthy and costly processes. And here, for example, like for drug developments over the entire cycle, it's 15 years, and it can cost up to $3 billion. And hence, generative modeling has been created to help exploring, for example, in that case, molecular active space more efficiently, or in the case of medical analysis, it's more like how to perform data augmentation for images. And I'll explain later on why this is a challenge and it is important. And in that context, generative adversarial networks, which will be the focus of my talk today, are an example of generative methods. They're not the only one, but this is one of the main example in especially for drug developments for such tasks. But they do suffer from various challenges in the classical sense. For now, what I will present you here is a structure which is called latent style-based quantum GAN, which could help overcoming these challenges. And my team, we really successfully implemented this quantum GAN on MOSES datasets, which is quite industry relevant for drug discovery. And I will present you some real quantum hardware sampling with promising results. I will also present you image generation task tested on, well, satellite data. So you could say, well, it's a bit far away from biomedical image analysis, but the pipeline is essentially identical. It's more like the data set which changes. And I will show you that these tasks and the experiments we've been doing with these data set hints at something very like peculiar, and that was not that's something we actually waited for at the beginning of these experiments, is a type of quantum exponential advantage for QGANs in a number of trainable parameters. Of course, there are challenges. The main one is that NISQ, so noisy intermediate scale quantum computers, are limited in circuit width and depth. We've also done experiments on trapline hardware, and these are slow, also quantum modalities. And training on quantum hardware is very costly. So the next steps, we want to investigate how to run on IonQ, how to perform systematic error mitigation and error suppression. I want to test also some modalities to improve, like constraining our generative modelings with conditioning. We want to also extend to larger data sets towards anti-cancer or AMR treatments, or antimicrobial resistance. And we want to do some testing on biomedical images as well. So that's the summary. Now let's see what's going on in details. So I start with one problem statement for drug design. So here, this is an image which show you the entire workflow to create a new drug, which goes from the first phase, which is drug discovery, to the clinical testing, to the approval for production. And all these phases take time and money. And I also want to stress, it's orthogonal to the discussion today, but I want to stress that, for example, last one, the approval for production could actually really cost you a lot and takes lots of time because it requires some regulatory approval, for example, from the FDA in the United States and so on and so forth. But the first step here, which is drug discovery, could take 7 to 10 years, depends on many factors. And even if you can identify in the vast landscape of potential targets something which seems promising, then you have to find the so-called lead optimization, which means how you formulate the drug to be ingested by the body. Is it like a pill? Is it like injection? Is it like a liquid? This also can just go to waste the lead you found in the first phase. And then you have the clinical testing, which also, of course, are quite complicated and costly and takes time. And here, I will be focusing on the very first part, which is to target identification and lead discovery, and how computer-assisted methods could help in that space. The second problem statement is medical image generation. Why do we want to use generative modeling for that problem? It's because if you want to use medical images for diagnosis, for prediction, so many important tasks for personalized medicine, you are always facing a scarcity of data, the sense that you have small amount of real patient data for further study, like classification, detection, and so on and so forth. And the reason is because, well, you don't have so many patients. Even if you have a handful of patients, the good data is not always there. I mean, you filter, so you have maybe, let's say, 200 samples, maybe 2,000 samples, but out of which only maybe half of them are actually clean. The image acquisition is complex, and the particular example of CT images for the brain, well, it's hard to get because they put patient at risk of brain damages, because I mean you're doing radiation exposure on the brain. So that's also the reason why you have small data sets, for example, for that particular set of images. And that's the reason why we would need a computer-assisted method to augment the small data set you have, such that later on you can use these bigger data sets augmented by synthetic methods to be used for, say, classification, detection, and so on and so forth, prediction also as well. So that's the second, let's say, problem statement. And for both of them, well, generative adversarial network is a method that can be very competitive. So what is a generative adversarial network? So it's actually two networks that you can see on the left-hand side, which are competing against each other. So the generator here, do you see my mouse, by the way? Just want to be sure of that. If you can tell me.
Yes, we can see it.
Great. So here's the generator whose role is to produce the fake data. Okay. And then it creates generated samples, which are then compared against real samples, which comes from the input training sets, which are then classified by the discriminator, which will tell, well, what do I get is real or is it fake? And you can see why it's a competing, or what is called an adversarial training, is because the role of the generator is to fool the discriminator, and the role of the discriminator is to catch the generator fooling it. And that's why I usually like this art forger analogy. Like, think about the generator as like an art forger. It's trying to create fake paintings that look authentic and then to gain money because you would sell it on the market. Now, the discriminator, the art historian. So its goal is to check the paintings, and with his knowledge or her knowledge, it's try to catch the forgery. And now the training is a catch me if you can game between the two, the art forger and the art historian. And the training is done, or is successful, if the painted forgeries are so good that the art historian, or here the discriminator, has at most 50% chance of catching it. So the guess ratio is really half-half, which means that at this stage, the generator, here the art forger, is good enough to produce realistic, new, here in that case, art, in the same style as the input data set, but still new. So that's the idea. So it shows immediately why it's good for data augmentation. So that's great. There are challenges with classical GANs, and that's the reason why I'm interested into its quantum extension. The first one is the training pattern can be very complex, and so classical GAN could sometimes just be stuck in the training process, and the adversarial process does not converge. The second important challenge is called mode collapse. And what is mode collapse? It's simply when the generator is stuck in the training in a subsamples of the entire diversity of the training set. So it becomes more and more efficient, but on a smaller, less diverse part of the training set. And that's why you call it a mode collapse. It collapses in a subset. So it misses the entire diversity, which of course, if you think in terms of generalization, when you want to apply your trained GAN on inference, then you are at risk of just not being able to generalize. The third one is so-called non-robust training. It's great sensitivity to the hyperparameters. And the fourth one is the Baron-Platus phenomena, which is when the gradients which are used to do the training, is becoming like the landscape is becoming extremely flat, such that the training procedure takes exponential time to reach the minimum. So, and in all honesty, you will see that this fourth one is also a very big issue for quantum GANs. So now the question is, well, okay, could quantum GAN overcome some of these issues, all of them ideally, but well, can we do better than classical GAN? So that's the question that I want to address in this talk. So what have we studied? We have studied what is called a hybrid quantum GAN, and also I will elaborate on the second point that you see in the title of this slide, the style approach. So hybrid means if you want to, let's say, if you want to make a GAN quantum, well, there are, let's say, three ways. Either you make the generator a quantum network, or you make the discriminator a quantum network, or the entire GAN becomes quantum, which means most networks are quantum. Okay, so that's the ways. But the literature seems to indicate that at the moment, the best or the most powerful GANs are the hybrid one, in which the discriminator is still a classical neural net, but the generator is replaced by a quantum variational circuit or parameterized circuit, which is what you see here on this slide. So the discriminator is still a classical net, but the quantum is composed of like quantum gates acting on qubits. Okay. Then you have measurements. The measurement outcome produces your fake data. Now you see you can improve on that. So that's the let's say the standard vanilla congan, and then you can add what is called conditioning. For example, in that case, it was designed for drug, where you have like some first layer in which you have a C which accounts for some condition on how to tailor your network for some properties of the drugs. For the training, you have different choices, which metrics you use for the training. And here, in all the results I will be presenting, in nearly all the results I will be presenting, it's using what is called the Wasserstein distances. So it's a Wasserstein GAN, which is the Erst-Mover distance between generated and real data, okay? Including also a gradient penalty in order to mitigate mode collapse. So it's what is written there, okay? So it's essentially compare the, let's say, the expectation value of the output of the discriminator against the output of the generator plus, well, some lambda times some like bounded expectation value on the gradient of the discriminator. So this gradient penalty will constrain how the gradient evolves during the training procedure. Okay. Now, the style-based approach was introduced in this paper with my colleagues. We introduced that in 2022. And it's something which is similar to, if you are familiar with classical GAN, the style-based approach in classical GAN. And the idea is you insert the random noise. The random noise is the input of the gates here in this circuit. Okay. And the goal of the training procedure is to transform the output of the GAN such that this random noise is transformed into something meaningful. Okay. Usually in vanilla or standard GAN, what is done is that this input noise is only introduced the first gates, in the first layer of the network. The style-based approach introduces the noise everywhere, in all the gates. And I say it bears the idea from classical GAN because it's exactly the same concept. In classical GAN, it's called data reuploading, which you essentially reupload this noise, input noise everywhere in the network. Okay. Now, why style and not just the vanilla one? It's because in our seminal paper in 2022, we compared the style and the non-style QGAN on a task which was for high energy physics with very non-Gaussian data, as you can see here. The goal was to do some data augmentation on these three distributions and their correlations, of course. And I just show you the plots to show you that it worked very well. And here, actually, it's really what you see. It's sampling on real hardware, so it really works. Back then, we used was what is called the Kullback library divergence, the KL, as a metric for the training and also for like evaluating the performance of our results. And just in a nutshell, the KL is a cross entropy between the let's say reference distribution and the generated distribution. Okay, and now you can see on the right-hand side, what I want to stress your attention on is especially on the KL results for the T distributions. And you see that the lower the better, by the way. Okay, well, in case of identical distributions, in principle, the KL goes to 0. And you see that in our case, for these experiments, we got 0.074 for the style QGAN approach, while for the vanilla one, we were like 2 orders of magnitude worse. So clearly here, we saw the improvement. And better than that, by construction, because the style-based approach has noise everywhere, well, it's an extension of vanilla QGAN. That the vanilla QGAN is a special case of style-based because you can always construct the vanilla QGAN by restricting the noise in the first layer. So just to mention that it's really an extension. So that's the reason why now more and more we're investigating style-based, because we saw that it seems to help compared to classical. Well, to standard QGAN, sorry, not classical QGAN. So What are the potential advantages of these quantum models with respect to classical GAN? So the first one is, okay, we work in a high dimensional space, the Hilbert space. And we all know that this contains nonlinear correlations and quantum correlation, actually. So it's a belief, or it's a common, let's say, ground that this should be suited to capture complex correlation in the data. Like if your data is like extremely complex with many correlations hidden in the data, well, I mean, if you work with a structure with naturally work with complex correlations, then it should be better in capturing them in the training procedure. Quantum modeling, not only GAN, but in other modeling as well, like for example, also like in quantum CNN, quantum reservoir computing, and so on and so forth, we've seen that it usually uses fewer training parameters. And I will actually come back on that point later on during my talk. For the robustness, we hope that QGAN are less dependent on the choice of the initial weights, so it would improve over that. We also think that there's a potential for better expressivity on compared to classical GAN, and it's somewhat mainly related to the first point I mentioned. And what is also very important, it seems that it leads to better generalization in the sense that you don't need too big a data set such that the generalization works compared to classical GAN. And especially this has been like studied in these two papers, not only for quantum GAN, actually, for quantum modeling. And this is an extremely interesting point, especially for medical images. Remember what I mentioned before, where for medical data sets, we expect to have very small, useful amount of data. So for that perspective, quantum modeling should be better at creating a powerful pipeline to do data augmentation. Well, I also talked about barren plateaus, and we should not forget about the curse of barren plateaus, which also exists for quantum machine learning. Okay, so for the task of drug discovery, here is a full pipeline using quantum GAN, but not only. What we'll also use here, in order to account for the very high complexity of a molecule, we first actually compress the information of this molecule into an abstract latent space composed of vectors representing the initial informations, but compressed, so the dimension of this latent space is smaller. And for that, a common method is to use autoencoder. So the idea is that you pre-train an autoencoder, which for that purpose is classical, onto this initial data set, which is composed of molecular structure. So for those who are familiar with molecular data set, here we have used what is called the SMILE inputs, which is an encoding procedure, how to go from this molecular structure that you see to an alphabet representing the structure. So here, for example, it's for the ibuprofen molecule. So you start with the real world data set. It's an input for the pre-trained version of autoencoder. So you train it on the data. So it creates an encoder and a decoder. So the encoder will project this molecule into this abstract latent space, producing what we call here the real features. Okay? And this will then be used for the training of the GAN. Okay? And in the end, after the training is done, well, the quantum generator is producing realistic latent vector. So it works in the abstract latent space. And then you use a decoder that you have pre-trained to transform this into real world molecules. And you see here in red, I have written advocate features, advocate validations. These I will talk about it a bit later on, but these are tools to, let's say, validate the chemical structure that you generate and act as a filter in order to, let's say, be sure that what you generate is chemically relevant. Okay. Are there any questions so far? Because I know this
Mhm.
can be complex.
Okay, let's see. I do not see any questions on the chat, but maybe someone would like to unmute and ask. Okay, I think we can go on.
So far, so good. I hope you follow me because I know there are many concepts at the same time.
Yeah, I think that for people with who have some experience with guns, it's still quite natural. So I think
It's
we
perfect.
can proceed.
So why the Latin style-based QGAN? Now, and that's where we start to answer also the question about man plateaus. So the style-based approach, okay, it's proven to deliver better results than standard QGAN, thanks to the data real plotting architecture that I showed you before. It's also better suited than direct QGAN for complex and large data structure. And this was studied in this paper, say for the first time, in the context of image generation. I will also come back to it later on. Now, and that is very important for the Baron-Plateau analysis. So essentially, it's also something which is still like a very active research area for quantum machine learning. Like if your circuits become deeper and deeper, well, the Baron plateaus will eventually, unfortunately, come out. So essentially, it's better to live with shallow circuits. That's the first thing. But it has also been shown here that for that particular structure, quantum GAN, style-based quantum GAN, using the latent space approach, that you can control the Baron plateaus phenomena and tame it down. So I don't say you can kill it entirely, but when you work in certain region of the initial parameter, um, then you have like an absence of Baron plateaus. Not everywhere in the hyperparameter space, but in many corner of this space. And this was studied in this paper. And this is a very good news for us because this is exactly the kind of the same structure that we are looking at. At some For that moment, the result I will be presenting you, it's without conditioning, but we really want to do it. Okay. What is important here that in the trainable gates, so if I come back here, in the trainable gates, we actually not use like, we don't use these, we don't use the usual affine formula with like the weights plus the bias, but we also use a nonlinear function to restrict the angles between 0 and 2 pi. The reason it's because during the training, usually if you don't restrict with this nonlinear function here, the 10h function, well, the angle will grow. And because you are modulo 2 pi, you can have what is called a quantum mode collapse when you come back to close to 0 and you're stuck there. So by preventing this, we also help again to prevent mode collapse further. So that's something that I think is very important. I see, Pavel, that in the chat, I see like 4 potential
Oh,
questions.
there was just a question about recording.
Okay, great.
Mhm.
Thank you. Now, what is a data set we've investigated to perform a proof of concept? So we use what is called MOSIS. So MOSIS is a pretty standard data set for like open source drug-like discovery. And it's based on a bigger one, which is called the Zinc clean leads, which comes actually from real world data. Some are even commercial data, molecules there. And so the Moses data set is actually a filtering of the bigger one. And it ends up with like around 2 million molecules. And then in the actually, Moses is even bigger than just the data set. It also contains more molecules, metrics, and ranking set. Okay. So the split is like around 1.5 million trained molecules and around 200 1,000 test molecules. Okay. For our analysis, we started small. What we did first is a random sampling for MOSIS. And we actually did our proof of concept right now with 12,000 molecules in train set and 4,000 in test set. And it's great because it helps us twofold: prototyping and validation. And the second thing, which I think I find it nice, is also a test of what I told you before, that QGAN are able to generalize better when working on smaller data sets. And it's exactly the regime in which we are right now. It's, I mean, still pretty big, let's say pretty big. It's not too small, like for images, for medical images, where it's only like 2,000 images or even 200 images, but it's small compared to the entire MOSIS data set. Okay, so I think that's a nice add-on in the study, let's say. Okay, this is a big slide. I will flash it for you. I will not spend too much time because it's a big one. So there are many metrics that could be used to validate or to benchmark the quality of the generated molecules. So we use some of them to train and to tune the VAE. Some of them were used to tune the GAN. Okay, so maybe the most important one that you should have in mind there is, of course, the novelty, fraction of molecules not present in the training set. Validity and uniqueness is quite important. The log P. The log P is a distribution of partition coefficient between two phases, what are called here octanol phase and water phase. Essentially, it tells you how soluble a molecule is, or let's say how affinity it has with lipid or not, or with water. And you want a good drug to have some affinity with lipids, because then it will enter the body and goes targeting properly the place where you want the target to be. But of course, it should also have some affinity with water, for example, especially if you want to inject it in the body. So usually good log P for drug-like molecules lie between 0 and 4, usually. Okay.
Okay, Julian, I have a question here. So maybe coming back to this validity and uniqueness, because as we can read, we want to maximize the fraction of the molecules that are not present in the training set. Because I was wondering when you showed the split of this RD-kit data set, it was so the proportion was something like 25%, 75% for the training and test, as far as I remember, which was quite large
Yeah.
for the test. And I was wondering what was the reason? Was the reason, or is the reason justified here that we want to maximize
No,
this
no, no.
fraction? No.
No, here it's a bit. Think about that in the data set. Actually, when they constructed the data set, they also used some tools from RDKit to filter the zinc down to the MOSIS, such that it's relevant for drugs. And that's also something we want to do here. We want to check that the molecules we generate in the pipeline are they relevant molecules from a chemical perspective, but also for a drug perspective. So that's what the validity and uniqueness here is let's say checking. You know?
All right. Okay.
So there is actually an overlap between novelty and this one, because novelty also tests the fraction of molecules not present in the training set. But here, the focus in the validity and uniqueness is really to check, to be sure that you pass this chemical validity check, which means that the pipeline, the GAN, may produce along the line sometimes molecules which are actually not chemically valid. It's because it's working it's working in the latent space, and then later on it's decoded in the SMILES. But the SMILES, you can write an alphabet of like atoms and bounds, which actually are nonsensical. And that's why the RDKit tool is used, is to actually filter and remove the ones which actually are nonsensical from that point of view. Is it clear now? I think
Yes.
the
Yeah.
use one.
Yes.
Great.
It's clear. Thank you.
Yeah. So here, I just want to show you an example of hyperparametric tuning for the VAE. So we tested different latent dimensions, 10, 20, or 40, for example. We tested also a different number of epochs. We used as an optimizer Adam, gradient-free optimizer, pretty standard actually for machine learning, and in particular for GAN. And we use also some scheduling here. We also played around with a number of layers in the encoder, with a number of hidden dimension, with some dropout layers. And down the road, this is the final set of parameters, not particularly important, but I just wanted also to show you some of these distributions, like this internal diversity, the log p. So you see the log p usually is between -2 up to 8. And of course, it's even better if you could generate stuff between 0 and 4. That's the reason why, as you can see, it's heavily picked towards 2. Of course, it's because of that. It's because you have here a drag relevant data set and things like that. Okay. Now, I want to show you the details of the quantum GAN architecture. So on the and the classical one. So the classical generator here is a succession of dense layer and some non-activation function, which are the leaky ReLU. Okay. And down the road at the end, we have a final dense layer to come from like a final dimension of 1024 down to the actual dimension of the latent space that we've studied, 2010, 2040. And the discriminator here is also the same structure. It's like a like dense layer, dense layer, dense layer, and then scoring function. Okay. The quantum one, well, it's a quantum circuit, and we've studied three different Ansätze for the quantum generator. Okay. The reason for these structure, so the first one is what will be defined here as a style default one. Here is shown for 10 qubits and 2 layers. So you see, you essentially start with the first set of single qubit gates, like parameters, rotation, and then it's like a scale. It's a scale of control rotation, okay, over all pairs of qubits. And this structure was just simply the one which was originally introduced when the style-based QGAN was introduced for the first time in the literature. The second is a bit of a variation around that. So it's quite similar. Maybe I should introduce the third one, actually. The third one is what is called a style bell. Here it's for 4 qubits and 1 layer. So it's essentially like some very basic entangling layer. So again, instead of a scale in the style default, you see here like all pairs of qubits are entangled. So you entangle 1 and 2, 2 and 3, 3 and 4. Then I also entangle 1 and 3, and 2 and 4, and so on. This comes from this paper from Maria Schul and collaborators in 2018. So here it's trying to have as many entanglement as possible. And the style simple here is a variation of the style bell. But as you can see, in style bell, you have next to nearest neighbors entanglement. For example, here between 1 and 3 or 2 and 4. While here in the style simple, we drop out this and we only use entanglement in the nearest neighbors. So we will study the 3 different structure and see how they perform. Okay, here are some results for the training of the pipeline with 5 qubits and 2 layers, and what is called dual readout is the way how you do the measurements. Because when you come back to the quantum circuits, so you have multiple layers. Here's 2. You can have 3, 4, 5, 6. And at the end, you do a measurement. Essentially, you calculate an expectation value. So either, for example, if you have a latent dimension of, let's say, 10, either you use 10 qubits and you perform just expectation value, let's say, of sigma x. So you're only measuring in the x basis. And you collect the outcome, this expectation value. So you have like a vector of 10 numbers. Or you work with 5 qubits. And now, same circuit, but you measure first time the expectation value of the Pauli x, and the second time the expectation value of the Pauli y. Okay, and you can do that. These are independent expectation values because they don't commute. It's perfectly fine. And you only use 5 qubits instead of 10. But you still have a latent vector, which is generated by the quantum generator of dimension 10. So it's a nice way to, let's say, profit from the fact that right now, well, the quantum hardware is limited in the number of qubits. So you can have a larger latent dimension with a smaller number of qubits. But of course, there is no Freeland theorem to actually collect expectation values on quantum hardware. You have to perform multiple measurements, shots. So if you use dual readouts, then you have to double the number of shots to get the same statistical accuracy on your latent vector compared to one single expectation value over 10 qubits. So no free lunch, but different advantages and drawbacks, let's say. So here, I just want to show you what happens on the left-hand side. It's a nominal model. It's an out-of-the-box from Moses, a classical GAN training. Okay, and you see the training as a function of the number of epochs, and we calculated 5 different instances, which means different random seeds for the weight initialization. So essentially here, what you can see is the effect of robustness. I told you before that we expect quantum GAN to be more robust. It is what you see here in that case. You see that the band, the 1 sigma band, is so much smaller, and it's more small. It's very smoother in the case of the quantum GAN compared to the classical GAN. So here, this is an improvement in robustness for quantum GAN. I also should mention, and it's what you see here, it's called ratio of discriminator to generator training frequency, equal 5. What does it mean? It means that when you do the update of the weights of the discriminator and the generator, you essentially update the discriminator here every 5 cycles of the generator, and not every cycle within an epoch. Same effects can be seen when we tune the model with hyperparameter optimization. So this seems to be a bit worse than the previous one, but it produces better results. And you can still see that, well, the quantum training is again better. Now, what about the metrics themselves? So after the training, I trained the entire pipeline, and I now compare on my like all of these like metrics I told you about. What you see in dark green are the best ones. In light green are, let's say, not the best one, but close to the best one. And in what I call in orange, like the really not good one, let's say, compared to the rest. And white is, well, something similar. And this is for latent dimension of 10 with 5 qubits on the left-hand side. On the right-hand side is for latent dimension of 20 with 10 qubits. And in the ideal case, so what you see here is not a training on the quantum hardware, it's a training with a quantum simulator. Okay. And I think these are interesting results because you see that the quantum GAN is very competitive and sometimes even producing better results, significantly for these metrics, which is called the FCD, which is an equivalent of what is called the FID score, but for chemical molecules. And what I want to stress is the number of parameters. The classical GAN has 705,000 parameters. Here, the big, let's say the most complex quantum generator we've investigated had 110 parameter. So it's really small compared to the classical one. So what does it tell you? It tells you that not only quantum GANs are overall, let's say, I say better, let's say competitive, and for some of the metrics better, and they are more robust than classical GANs, but they are obtaining this result with far less trainable parameters, which in turn is helping us in what I call explainability, or trying to understand where the effect comes from. When you have so many trainable parameters, it's very hard to actually understand, let's say, which part of your network is actually driving the result you see. But if you have a much more compact let's say in that case quantum, but let's say networks, machine learning networks, with far less trainable parameters, it's much easier to track down where the effect comes from. And we in turn think it could help for generalization. So that's what we got. And I think that's our pretty nice results. This is also the distribution of this metrics. I want to stress the log P metrics, for example. Overall, I would say that the quantum model is performing better than the classical one. But more importantly, also again, if you look, for example, the yellow line here is the classical GAN, and you also see the band. And again, it's a reflection of the increase in robustness. You see that the same band is much smaller for all the other lines that you see, which are the quantum ones. Okay, significantly sometimes. So this is also quite promising results. And last but not least, we also tried inference on the quantum hardware. So what happens when we go from like the ideal to an actual, let's say, quantum computing system? We did this experiment on IBM Kingston system. And as you can see, we got a degradation in performance sometimes. Sometimes, quite interestingly, some improvement. But of course, it's just one experiment. So to be really more robust, we should perform this multiple times, different random seeds to really assess. But I want to stress that the molecules you see here are new molecules, which have never been seen in the training sets. And they are all passing the RD-KIT filters, which means that these are chemically valid molecules which are relevant for direct design. And you see many of them are in the good range as a SN of log P, except from this one, for example, or this one, which is slightly off, but all of the others are between 0 and 4, as I wanted. So I find it pretty interesting, because this comes from an actual quantum computer, and this is chemically relevant, and especially for direct design. So it's pretty cool. Okay, challenges. Not everything is perfect. So we have challenges for scaling. The first one is the coherence time and the noise on the real hardware. All of the results I've presented so far for this pipeline is without error mitigation or error suppression. And it would be interesting to implement that and see what's going on. Of course, another very important is the training was done on simulators. So especially beyond 20 or 30 qubits, it becomes impractical. But in turn, it becomes interesting, because that's the regime in which you want to work, in which you need the quantum hardware. But then it means that you have to optimize and change the training procedure, especially calculating the gradients, such that you really are efficient on the quantum hardware. And okay, this is something important for that particular use case, but it's a general statement for quantum machine learning. how to obtain efficient and say fast calculation on gradients on quantum hardware. The third point, which is a challenge in scaling, is okay. It would be nice to test that on trapped ion systems, which are, let's say, notoriously known to be in better quality than superconducting qubits, and they have all-to-all connectivity, which means that when you transform these ideal circuits that I've presented you to the actual circuits mapped on the machines, well, in principle, the circuits will stay more or less the same. You don't increase the depth. While on superconducting qubits, you don't have all-to-all connectivity. So you have like addition of swap gates in order to bring down close the qubits which are talking to each other in using these like control rotation. So the issue is like trapped ion are very slow. And for example, one sample here needs 40 seconds to be created on this machine, the late state-of-the-art IonQ machine, versus 4 seconds on IBM. So it's like a factor of 10. So here, of course, we need to work a bit on that.
I have a question here. So
Yep.
actually, yes, you said that for the reasons that you presented, the inference was on a 5-qubit computer from IBM, right? So for this inference, the training was also on a 5-qubit computer, or is it
No,
possible
no, no.
to,
We we
no?
we we we, we did the training. We reuse the same trainable parameters that were trained on the quantum simulator, but the inference was on the quantum
Okay.
hardware.
Okay, so the training was on a simulator, but was it also a simulator of a 5-qubit? Yes.
Yeah, yeah, yeah,
Okay.
yeah, yeah,
All right.
yeah,
Hmm.
yeah, yeah. It was a similar in the 5 qubits.
Okay.
Indeed, indeed,
And yes,
indeed.
have you maybe observed any advantage of using more qubits for this?
Well, in that case, for example, let's say a bigger latent dimension, this
Hmm.
you see that the results were well improved everywhere. So yes,
Okay. Yes.
uh,
Hmm.
but it's an open question. Do we need? I mean, what happens if we increase even more? Maybe at some point it's too big. So it's let's say at the moment for that use case, it's unclear where the best latent dimension lies. But clearly 20 and hence 10 qubits is better than 10 and 5 qubits,
Hmm.
as you can see, with improvement over all spectrum of the metrics. Yeah.
Okay. There's also a question, what's the reason behind the slow behavior of IonQ? Is it a hardware or
Okay.
algorithm? Hmm.
No, that's like, here it's the hardware. Like it's the same algorithms on two different hardware, and it's trapped ion are known to be notoriously slower. It's in their design. It's a design right now with the atoms they're using. They're using ytterbium atoms. So we know that the next generation should use barium, which are a bit faster, but still slow enough. So there is still lots of work to be done to make it really faster. And I think it's especially important for FTQC, fault tolerant quantum computing, because when you want to do the error correction, you need to do multiple mid-circuit measurements to measure the syndromes. And if your operations are slow, that's a bit bad. There's another reason, which is specific to IonQ at the moment, is that the operations on trapped ion of IonQ are sequential, in the sense that for IBM, you can perform, let's say, operations in parallel on the different qubit line. So, for example, the 1-qubit gates, for example, on qubit 1 is done in parallel of the 1-qubit gate operation on qubit 2, not for IonQ trapped ion computers. I know that Quantinuum has moved forward on that, now allows for what I call parallelization of four qubit lines. I know that IonQ will, for the next generation, allow for a bit of this parallelization, but at the moment it's not there. So it adds on the slowness of the entire pipeline.
Okay, let's see. No, there are no more questions, so we can
Great.
continue.
Thank you. Thank you. Okay. Now I want to switch because I told you that I wanted to talk about drug design, but I also want to give some hints about what happens with image generation and what can we learn about QGAN with image generation. So in 2024, there was a study of latent of the capacity of the capability, sorry, not capacity, capability of latent style-based architecture to generate high-quality images. Okay, this is this paper from colleagues at CERN. So they study NIST, fashion NIST, and SAT4 datasets. So what is SAT4 dataset? It's an open source satellite dataset with images of 28 times 28, and they have 4 channels. So the usual red, green, blue, but also the infrared one, the like near infrared to be more precise. So here is, for example, an extract of the data sets. So it's essentially 4,000 training image patches plus 100,000 test image patches, which are covering 4 classes of images, like barren land, such as the one you see here or there. Okay, trees, what you see here, for example, or there or here. Okay, you have like grasslands. So grassland would be, for example, this one or these ones. Okay, and the rest. So anything which does not belong to these categories. So for example, here cars or like highways or buildings. This is in the 4th category. Okay. So what did they do? What did they use as ansatz for the quantum generator? So it's another one. Here I display it for, let's say, 12 qubits. And the reason is because this is the same ansatz that I will also use for the next study I'll be presenting. And it's based on what is called universal SU4 2-qubit blocks. And I refer to this paper. So you see these blocks here on the first 2 qubits, for example. So you have like so-called U3 gates, which are universal gates, 1-qubit gates, parameterized by 3 angles. Okay, then you have like a C naught, which perform entanglement. Then you have like rotation gates, Y and RZ, which are parameterized. Again, a C naught, again, a RY, a C naught, and again, these universal ones. So this block here is a universal SU4 2-qubit block. And so essentially the ansatz here is like replication of these everywhere. First, second qubit, third, fourth, and so on. And then just displacing it slightly to entangle 1 and 2, to entangle 3 and 4, and to entangle the 11th one with, well, with the 0th one. And then here, again, some RZ, RY layer, and then measurements. Okay, that's the ansatz. So it's deemed to be pretty expressive because it's very general ansatz. Okay. So what happened? So they used, which is very common, and like everyone uses this metrics to measure the quality of image generation. It's called the Freshe. Oh, sorry. It's called the Freshe inception distance, FID. It's measured the quality of the generated images, and the lower the FID is, the better. Okay, so it's essentially the L2 distance between the mean vector of the distributions of the images plus, let's say, the covariance of between these two distributions. Okay, and they compare the Latin style quantum GAN approach with 2 layers and with this ansatz. This has 3,300 parameters against a classical state-of-the-art GAN with this particular structure. Okay, so 2 dense layer. First one with 100 nodes. The second one is 50 nodes, which has roughly double the parameters. And they obtain competitive FID scores, as you can see. Okay. So here it's for latent image of 20, 10 qubits to layers. Okay, so we with my colleague, we started from there and we asked ourselves the question, okay, first, could we do better? What happens with more layers? And so we started to perform an analysis of the number of trainable parameters. So what we call the capacity of a network. Okay. And so with my colleague, and we released the results like a few weeks ago, we studied for this use case, SAT4 image generation. And we used a similar setup as for the drug discovery analysis. So we work in the latent space with a pre-trained VAE, and we use a style-based quantum GAN to generate these SAT4 images. We fixed the latent dimension to 24, so we worked with 12 qubits, and we looked at quantum layers between 2 and 8. So 8 starts to be pretty deep. So just for information, this is the structure of the autoencoder. So no surprise for the people who are seasoned with AI, we used convolutional neural nets for the autoencoder because we are working with images, and convolutional neural nets are very, very efficient with images. For the generator, so either we use the quantum generator, and I've shown you the answer, or we use the classical generator with like these two hidden layers, so two hidden dimensions. And the structure of the discriminator is pretty similar. Also, it has two hidden layers. So what we did is we play around with a number of quantum layers, but we also played around with a structure of either the classical generator to compare against classical GAN, but we also play around with the structure of the discriminator. So that's the setup of the experiment, okay? 24 the latent dimension. We have this number for the linear layers. We look at generator. We had also this number of epochs. We also play around with this number of landing rates and so on and so forth. What I want to stress is the goal here of this analysis is to perform a scan on all these hyperparameters. Okay, so for example, we investigate for the classical generator. At least the minimum was like this structure 5025, which corresponds to like around 2000 trainable parameters, until up to 400 to 200 for the structure, which amounts to like 90,000 parameters for the classical one, for two quantum layers. And when we compare to, let's say, 8 quantum layers, you see that the numbers grows like significantly. Okay, and the goal is to perform a training such that we have a stable training, we have low FID score, and the FID scoring is also stable, so we can trust it. And these for us define an optimal GAN structure. And in turn, we want to compare the capacity of this optimal structure, or the number of trainable parameters, between quantum and classical. And this is the results we got. And I think these results are very compelling. So we performed a threefold experiment, so 3 different random seeds. I really want to stress, and that is very important to interpret the results. In this scan that we did, the pre-trained autoencoder is the same. So we really change only the GAN part, such that we disentangle with potential effects from retraining the autoencoder, which would lead to even better results. No, the autoencoder stays the same. So we really just look at the effect of changing the structure of the GAN. And as you can see, so the x-axis is the quantum generator capacity. So essentially the number of trainable parameter for our quantum GAN, which were in turn calculated out of the number of layers. And the y-axis is the number of trainable parameter for, in blue, our discriminator, or in green, the classical generator, and the optimum that we get for these tasks. Okay, which means that these points here, they correspond to structures of classical GAN and quantum GAN, which give equivalent FID scores, or close, very close. But as you can see, the number of trainable parameters for the classical GAN is exponentially bigger than for the quantum GAN, because this is an exponential feat. Which means in turn, if I go deeper and deeper and deeper, if I work with, and you reverse the thinking, if I work with very deep classical GAN and I obtain super nice results, well, I could obtain equally good results and potentially even better results, as you've seen for the drug discovery case, but with a quantum network which is exponentially simpler than a classical network. And that's why I call this a hint at the quantum advantage, or at the type of quantum advantage, because it means that you are working with much more efficient network, because they are much smaller. And in turn, it could become a real quantum advantage in the sense that, well, think in the future when the quantum systems, the quantum hardware becomes even better, and we work with, say, with quantum system of thousands of qubits, when you could extend the quantum generator capacities to the range of, let's say, 10,000 parameters or maybe 100,000, which would in turn be completely untractable for classical GAN. So that's maybe even hints at the future, let's say, true quantum advantage. We also perform sampling on real quantum hardware because we wanted to see how the real hardware would perform. And this is the output. So here we sampled 10,000 images. We used IBM Pittsburgh hardware. So it's a 156 qubit IBM Heron system. And it compared the output from the noiseless quantum simulator to the output from this machine, where we use 4,000 shards, and we use the default readout error mitigation. And the third row here is resilience level 2, which means on top of the level 1, you also have gate trailing. You also have zero noise extrapolation error suppression method. Okay. And well, by eye, the results are pretty similar, which in turn I find that pretty nice. But of course, the quantum noise introduces some FID degradation, as you can see here in the number. When you look at the FID here from the noise assimilation, it's 109, and well, with the quantum hardware, it degrades significantly. I also want to stress we wanted to see if we could tune this entire structure to make it better than, for example, what was in the literature in the 2024 paper. So just recall this number, 109 here, and just wanted to show you that here, okay, comparison is not one apple to apple, but here you see the FID scoring was much bigger. So which really means that this produces better results. Okay. We also investigated the effects of error mitigation. So here you just see like the sampling of latent vector. So it's just like 20 random sampling of the latent vector. So it's before the decoding, essentially. In black, you see let's say the ideal case. And in blue and red, you see the output depending on whether it's level 1, level 2. And clearly, you can see that not only, well, increasing, of course, the number of shots helps to reduce the statistical error, that's clear, but also the error suppression really help to bring back closer to the black line the output of the quantum generator. So here, clearly, error suppression and error mitigation helps also to squeeze more, let's say, relevant information out of the quantum hardware. of course, questions. What happens with the medical image data set? Because that's what interests me. Do we get the same exponential capacity scaling? We are working on that. Are the results robust against changing the latent dimension? So do we get the same behavior with, let's say, 20 or 16 latent dimension? And what I think even is more interesting question is that, okay, we fit the output with this exponential fit function, a times exponential b times x. And what drives the shape is, of course, b. So a is just a rescaling factor. So I expect the A to change dramatically if I change the data set or if I change even the structure, the latent dimension. What about B? Could the coefficient B be a universal one and a characteristic of the quantum ansatz? So I don't have the answer yet. But if the answer is yes, which means, let's say, if when I train this quantum GAN on a medical image data set, which is completely different from SAT4 data. Let's say smaller data set. Let's say I'm looking at a completely different type of images, different classes, different channels, and I get still an exponential scaling with the same B coefficient or very similar, then it makes the result even more interesting because it means that maybe this is a universal characteristic of the quantum circuit and not linked to the use case of the task at hand. So it's still a work in progress, but I think this is very interesting. So I'm at the end of my talk. So I hope you've enjoyed it. So again, just to flash out the executive summary once more. And I think there are many exciting things to be done and lots of work ahead. Particularly excited to extend the pipeline for other very relevant applications, such that targeting cancers or trying to solve antimicrobial resistance. So I'm very excited about that. And I'm very excited about looking, which is something you can consider a little bit more fundamental or more close to the mathematical structure. I'm interested in checking these questions for this universality and these hints of potential quantum advantage. And with that, I really want to thank you for your attention, and I hope you've enjoyed the presentation.
Great, thank you. Thank you, Julien, for this great presentation. It's time for questions. Let's see. There is one question on the chat from Zahid. Recently, quantum transformer like Quixer are being used. Have you compared QGAN and Q transformer?
So it's a very good question. No, obviously not. It's actually part of my agenda to investigate other quantum generative modeling, for example, quantum diffusion models, and I also would like to investigate quantum transformers for sure. So yeah, the answer is no, not yet. Now, it should also be said that for these particular use cases I presented, even on the classical side, GAN are pretty much part of the state of the art, even if we can always discuss. But for drug discovery, GAN are pretty much a state of the art. Of course, for image generation at large, not the case. Here, clearly, it's not the case. It's more transformers and diffusion models. But yeah, I would be very excited to investigate the performances of quantum models for such models. Yeah, for sure.
Okay, good. Thanks. Do we have more questions? Okay, so I have one actually, because you also mentioned about this inference time, which is quite large in case of the quantum computers, so both IonQ and IBM. Do you see that in the future it may change, that there are chances that in the future the generation can be faster? Because how does it compare to the classical guns?
Oh, that's a good question. Now, okay. clearly on simulators, the classical inference is much faster. But
Mm-hmm.
in turn, it's because when you have more and more qubits, I mean, it's exponentially slower to simulate more qubits.
Mm-hmm.
That is a given. Now, in turn, on the when you go on the quantum hardware itself, first, there are ways to improve the pipeline to make it more compliant with the entire, let's say, quantum pipeline on the quantum hardware. For example, on IBM, and to be even faster there. Um, and now on the hardware itself, there are improvement year after year on the speed of the gate operations, which in turn are, as I said before, needed anyway for quantum error correction. So yes, my expectation is that the inference time will be at some point much faster than what we see today, what I have presented you today. That is a given for me. Now, how much faster? It remains to be seen, of course, but it will be clearly much faster.
Mm-hmm. Okay. And do you have a comparison what's the current time in the case of classical guns, not the simulators of these quantum guns, but just
Uh,
classical guns? I know that the classical guns have other weaknesses
Real,
like
yeah, yeah.
robustness for sure, but I'm just wondering what can be the difference in the inference speed.
Oof. I didn't record it, but I'm trying to
Okay,
remember when I performed the inference.
no worries.
Let me. No, I honestly I didn't remember.
Ah, that's fine.
Mm, I remember. Also, that's something I want to stress. Another very important element, maybe. Um, it was slower when I did the inference for the drug discovery than when I did it for image generation, for example.
Mm-hmm.
And here also there is another reason, which is the SDK that we used for the image generation. It's pretty. Let's say we really try to squeeze in the best, and it was implemented in JAX. While our code right now for the drug discovery is still implementing Torch, and you all know that JAX is just much faster than Torch. So I'm also expecting here sizable improvement in speed when I do the implementation of the drug discovery in Torch, for sure. Here I'm really expecting it because we've seen that for the image generation. We started with Torch and then we went to JAX. It changes everything.
Okay, good. Thanks for the answer.
I have a
Do we have
question.
more? Yes, Radu? Mm-hmm.
Please.
Did you use quantum simulators larger than 10 qubits?
Yeah, well, we did for the image generation because it was 12.
Mhm.
So okay, it's not significantly larger, but yeah, we did. And we have plans to actually go to 20 or even more using
And
GPUs.
how do you plan to do that? Because if you do that in Qiskit, it's impossible.
We don't use Qiskit.
Mhm.
The entire pipeline that you've seen, we've been using penny lane
Mhm. And you are using the GPU
because penny lane is just the
simulators.
best, right?
Mhm. So you are using the GPU accelerated simulators?
Yeah, well, when we go to more than 20 qubits, we use a Lightning GPU, indeed.
And is this practical? I mean, did you do some test?
Yeah, yeah. No, it works. It works.
Okay,
It does
thank
work.
you.
Yeah, of course, then it needs a good GPU and so on and so forth, but it does work.
Thank
It
you.
does work. Yes, yes, yes. But you're
Okay.
right. Qiskit is not. Yeah, we use penny lane. Penny lane is just good for quantum machine learning. I find really, really, really
Mm-hmm.
efficient. So that's the reason.
All right, thanks. Do we have more questions to Julian?
I hope that everyone is excited by the exponential capacity scaling because really I was
Yeah.
excited when I saw that.
And by the way, so thanks for sharing such recent results, actually. So even some results that I understand haven't been published yet, right? Or
They are an archive.
Or archive. Okay.
Yeah, they're on archive. You can find them in archive. Of course, they're not yet in a
Okay.
journal, but they're on archive.
Yes.
And yeah, we are working on on medical data sets to make the results even more robust. But
All right.
I can't yet present the results.
Yeah.
Let's say at the moment. But we do have very nice results. But
Yeah.
I can't say more.
And anyway, it's also quite fascinating that you found a use case for which you can, let's say, demonstrate some advantage or benefits of using quantum computers or simulators, quantum computers with only several qubits, actually.
Yeah, that's a good statement. I mean, something that, yeah, again, as I said, it's not a real quantum advantage in the sense that,
Mm-hmm.
I mean, it's comparing stuff that are still possible with classical, but it's more the extrapolation of the curve. Like this exponential behavior means that when you scale it, well, you enter a regime of quantum advantage for sure, because then, I mean, when you have the equivalent. So if I really come back to this picture,
Mm-hmm.
clearly there, if you here you see it's limited to up to 2,800 parameters, so 8 layers. But imagine you have not 8 layers, but you have 20 layers. So
Yeah.
clearly you will be in the regime of, I don't know, still a small amount for the quantum generator, maybe 15,000 parameters, something, because it's a linear progression. So
Mm-hmm.
it's even less actually. Like this corresponds to 8 layers. So if I go to 16 layers, essentially, I am at like, okay, 6,000 parameters, more or less.
Okay.
But this is exponential for the classical case, and you see that very quickly you are exploding the number of parameters in the classical side, like literally exploding it. You enter in the billion regime. No, sorry, no, yeah, the billion, yeah, you enter in the billion regime. So it's like it's becoming as big as like the LLM. So when we see
Mm-hmm.
that the training is taking an enormous amount of resources and energy, but the coin one is very small.
Okay.
So yeah,
Good. Thanks. All right. Do we have more questions to Julian? Last chance to ask. Okay. If not, then Julian, thank you once again for this great presentation and also answering the questions that we had. Uh, before we finish, let
thanks a
me
lot.
yes. Before we finish, let me just share my screen for a while, just to make a few last announcements for today, and because we already have some plans for the next meetup. Okay. Yes. So this is still today's meetup. Okay. So we would like to thank our speaker for a question. Let's see. So there's something on the chat. No, that was just thanks for informative talk. Yeah, that was great, really great. So thanks, Julian, once again. And yeah, everyone, if you enjoyed this meetup, we invite you to stay in contact. You can follow our social media profiles, join our groups, and so on, and join our Discord server. As I said, we'll try to upload the video recording to our YouTube channel, so you can subscribe. We'd also like to thank our strategic partners once again, Sonovero R&D, Quantum.io, Onyx, Cogit, AIQ Lab, and ThinQubit, and our honorary partners for supporting us. And if you like, you can also donate our activities, especially if you are in Poland. You can donate 1.5% of your tax for our activities. And this is the final announcement. We invite you to the next meetup on February 19th. Emil Jacques from Bait Tech will give a very interesting talk as well about simulating high accuracy nuclear motion Hamiltonians in discrete variable representation using Walsh-Hadamard QROM with fault-tolerant quantum computers. So I heard that it's also very interesting and quite novel research and result. So we are looking forward to the next meetup. We hope that we'll meet again in a few weeks from now. Um, So thanks once again. I will now stop recording. And as this was the first meetup in 2026, I would also like to wish everyone Happy New Year, Happy 2026. And I hope that you will
Happy New Year
enjoy
to
and
you.
attend our next events. Thank you.
Thanks, everyone.